Should I go? Okay. So hi everyone, I'm Wen Song. I'm an assistant professor in the Hildebrand Department of Petroleum and Geosystems Engineering here at UT Austin. And so I wanted to show some of the work that our group has been working on in terms of enabling the sustainable energy transition through recovering rare earth elements in an economic manner. And so this is a collaborative project between myself and my collaborators, Don DiPaolo, Lax Minarayan Raja, Thomas Underwood, Jay Banner, and Ashok Sapkar. And so we've brought together a team spanning, petroleum engineering, aerospace engineering, and engineering mechanics, the College of Natural Sciences, and the School of Geosciences and School of Public Policy. So the broad motivation for this work, and the previous talk kind of set this up pretty well, is that as we start to transition toward a energy infrastructure that has relatively low carbon intensity, we're going to need to effectively wean ourselves off of these fossil fuel heavy resources and more towards kind of these renewable systems. So for example, wind and solar, and as was previously discussed, these are intermittent resources, and so we're going to be needing energy storage at scale. And so, for example, lots and lots of batteries, and an important aspect of the low carbon future is going to be in the electrification of transportation, so vehicles. And so one of the key major bottlenecks for this transition currently is because of the lack of access to the minerals, so the material components that make up these technologies. And so, if we're talking about, for example, implementing these wind turbines that are going to need massive volumes of magnets, or for example, grid scale storage, where we're going to be needing lots and lots of lithium and other minerals, we're going to need to produce these minerals at scale. And so here you can kind of see that over the past 30 or so years, the global production of many of these minerals, so for example, here I've shown the rare earths, but these have effectively been dominated by one country, and that has been China. So you can see in the red, the US used to have a pretty significant amount of production, but that has since tailored off, mostly because of the cost and the environmental impacts of current technologies for processing these materials. And so you can see that effectively this market has been dominated by China. This is a picture of the mine out in Inner Mongolia. So you can see that, effectively we have to clear off the land, we have to dig these massive open pits. And so this is clearly an environmentally deleterious process. And then the subsequent processing is also reagents heavy. And the other key aspect is that because of the dominance of a single country in producing and manufacturing and processing these minerals, we're highly susceptible to price fluctuations. And so here, for example, you can see that the cost of dysprosium shot up about tenfold overnight because of trade, export limitations. And so here, the goal is to really look at alternative resources that may potentially, give us some stability in terms of securing the domestic supply chain. And so what we've done here in this project is look and assess various different domestic resources for various critical minerals. And so here, for example, in this map on the left, what you're seeing is effectively the total critical mineral concentrations across the U.S. based on coal-based resources as well as produced brine resources. And if we break this down into the rare earths, you can see that kind of the Appalachian region has quite a bit of rare earth concentrated there, and as well as kind of the Wyoming kind of Powder River and Green River coal basins. Similarly with lithium, you can see that there's pretty significant lithium being produced out of brines across the US, so in Texas particularly, and kind of in the Bakken areas. So this is quite exciting. And so what our proposed technology is to take these potentially unconventional mineral-rich resources and then extract that and separate it. So here we have an initial extraction process that is going to be mostly reagent-based, and then we'll take our kind of rare earth concentrated solution and feed that into a separator stage. So that's the system on the right here. So in order to do this, we first decided to focus in on the coal fly ash resource. And so this is really a waste material that, is a product of coal combustion. And so we've, been doing this for the last 100 or so years in the US at a pretty significant scale. And so, we effectively have mountains of this waste material that's been accumulating. And so, here I have a map of kind of the major coal producing provinces in the US. And so, again, the Appalachian region, the Illinois basin, and then kind of the Powder River and Green River basins close to Wyoming. So these are kind of the areas that we've been interested in exploring. And so the idea here is that instead of allowing for these mountains of ash to just, act as an environmental pollutant, for example, we have significant acid mine drainage around many of these disposal sites. So let's actually extract the minerals that are contained within the ash particles and turn that into something useful. So for example, magnets or computer chips that are going to be required to operate, for example, our vehicles and things like that. And so what we've done here is taken samples corresponding to coal that was extracted from the Powder River Basin, the Green River Basin, and the Illinois Basin out here. And what we find is that the ash from these regions contain relatively elevated concentrations of rare earths, so upwards of, on the order of about 1,000 ppm. So that's pretty exciting and significant. And so now in order to actually understand how to actually extract the rare earths out of these fly ash particles, we have to first know something about these particles. And so here we've performed some spatiochemical characterization of these particulates. And so here, for example, this is a single fly ash sphere. So these are little glass balls effectively that are on the order of, tens of micrometers in size. So they're very small. And they're mineralogically heterogeneous. So you can see that, if we conducted bulk mineral characterization in this table on the bottom here, you can see that the fly ash from the Illinois basin is relatively rich in silicates, right? So about half silicates and a pretty significant fraction of aluminosilicates as well. Whereas in the Green River basin, the fly ash here is predominantly, silicates, but also calcium oxides. And so this is a material that is highly susceptible to dissolution. And so that might tell us something about how to design the reagents around this. If we do further elemental characterization, we can see that actually, all of these particles are relatively enriched in all of the rare earths. And so that's quite exciting. And there's a significant amount of, elements that are valuable. So for example, praseodymium and neodymium. So the next thing that we did was to just perform kind of a bulk experiment in terms of, designing the reagents that are going to be used in these extractive processes. And so here we've taken, I'm showing data from the ash from the Illinois basin and the Green River basin. And so if you'll recall, the ash from the Illinois basin is effectively silicates and aluminosilicates, whereas the ash from the Green River Basin is elevated in calcium oxide content. And so here what we see is that the silicates-rich ash, so these are effectively the glassy spheres, really need to be dissolved using this HF, so hydrofluoric acid dissolution process, whereas plain leaching is going to, in the blue, is going to result in very low recovery. On the other hand, the Green River fly ash particles that are highly elevated in calcium oxides are extremely reactive and susceptible to dissolution with a weaker kind of reagent system. And so here, using aqua regia leaching, we're actually able to recover, upwards of 80% of the total rare earths available. So that's quite exciting. And so why does this happen? So here I'm showing some particles that we've taken from the Green River Basin. So here you can see that the yellow are the silicon, so that indicates the silicates. The orange and yellow together is, or the red and yellow together is orange, which is aluminosilicates. And the purple are the calcium oxide rich particles. And so you can see that basically after the leaching process, all of the calcium oxide particles are effectively removed or dissolved, and only after the heavy kind of hydrofluoric acid dissolution of the silicates do we remove the aluminosilicates. So here, this is giving us a clue as to what's going on within the particle system itself. And so again, we want to understand where the rare earth elements are actually distributed. And so here in this table of pictures, you can see that, so these bright white spots are actually the rare earth bearing minerals. And so you can see that, there's a distribution of them between the silicate rich particles, the aluminosilicate particles that can either be dense, so in other words, non-porous, or porous aluminosilicates, where there could potentially be reagent access to these internal structures where the rare earth bearing minerals are. And then lastly, we have these discrete rare earth particles that are kind of just floating within the fly ash particulates. And so what we find is that effectively after the leaching process, the only rare earth bearing particles are the remaining are the silicate and the non-porous or the dense aluminosilicate particles. And after the hydrofluoric acid dissolution process, we only find a few rare earth element grains remaining, and those are effectively all silicate particles. And so what's going on over time is that you can kind of see here in this table. So what we've done here is developed a microfluidic visualization system where we can embed these particles and then observe what is happening, how they're evolving as we expose them to various different reagents. So here on the top row, we have kind of the initial state of these fly ash particulates. And so here we have a silicate particle, right? We have a non-porous aluminosilicate sphere. We have a porous aluminosilicate particle, and then we have an iron-rich sphere. And so what we do here is apply kind of our weak acid dissolution or leaching process. And so you can see that effectively the bulk structure of these particles remain unchanged. And so the key difference here is that in the aluminosilicate spheroid, we actually are able to access the internal pore structure because it is connected porosity. So that's pretty interesting. And so now, using all of this understanding, we can then kind of design various different reagent-based extraction processes, and especially by minimizing the amount of reagents that we'll need here. And so what we can effectively achieve is something on the order of about 80% recovery of the total rare earths available, which is quite exciting compared to kind of this dotted line, which is the current state of the art, which is something on the order of about 15% recovery. So this has been pretty exciting on the extraction side. So now just coming back to our overall technology, right? So now we're able to produce a rare earth enriched solution that we can now feed into our separations stage on the right here. And so what we've done here is we've started out with with some modeling work. So here we wanted to use an inductively coupled plasma to effectively ionize all of the atoms that we're introducing into the separation stage, and then use electromagnetics to separate the rare earth species from one another. And so here, kind of the main questions that we wanted to address are: what are the optimal geometric and operating conditions? So, for example, pressures to achieve a stable plasma here. And then the second question is: what is the fraction of the rare earth species that we can actually ionize at these, under these kinds of conditions? And that, of course, is going to translate into how much we can actually yield out of this separation process. So here, this is a picture of the experimental setup. So we have a quartz tube in the bottom here. So this is kind of half of the picture. We're doing this, assuming radial symmetry, and we have some effectively some coils around this to generate, electromagnetic energy to ionize the fluid that we're going to introduce. And so in terms of this numerical experiments that we've performed, we've done a bunch of parameter space mapping. So we've looked at different pressures, powers, flow rates, and tube dimensions effectively. And what we find is that the ionization fraction of the rare earth elements is strongly dependent on the pressure of the system that we're operating at and the power density that we're adding into the plasma. And so what we find is that the higher the pressures, the higher pressures are able to support higher ionization fractions, and the smaller tubes or discharge dimensions are able to support higher power densities. And so because of that, we've chosen to effectively do these experiments, numerical experiments, in kind of capillary tubes that have, are on the order of millimeters in diameter. So in order to actually run these simulations, we needed to, have a good understanding of all of the reaction mechanisms. So here in this table is an example of all of the reaction mechanisms that go into such a simulation. So here we've chosen argon gas as our carrier fluid material, and then we've used cerium as kind of a surrogate rare earth element for our ionization experiments. And so here are some results of those numerical simulations. So here, again, we're introducing basically a flow of fluids, right? So our argon is our carrier gas, and we're basically spraying in some of the solution that's coming out of the extraction stage. And so coming out of that, we're expecting something on the order of about, or measuring something on the order of about 10 to the minus 5 mole fraction of rare earths. This is purely as if, dependent on how much water is in the system. So we can play with this number relatively easily. But what we find is that for, the different pressures, here we're using a constant power in all of the cases. And as we increase plasma density, as we increase the plasma density with increasing, as we increase the pressure, we find that we're increasing the plasma density. And so that therefore we can anticipate a higher throughput for the ionization of the rare earths. And the plasma itself is actually getting constricted for higher powers. And so that enables basically the rest of the rare earths to just slip through and not become ionized, which is not good. And so here, these are basically demonstrations of that. So here you can see this is the concentration of the cerium element, and here is on this bottom row are the concentrations of the cerium ions. And so you can see that effectively the ionization fraction kind of tapers off as we pass 1 torr of operating pressure. And so for the experiments, this is what we've been able to find, is that 1 torr is kind of our operating condition that we're going to be using. And so now, using this understanding, we're going to basically kind of redesign our experimental setup a little bit. So we'll have a shower head kind of configuration where we're feeding in the ionized rare earths, and then we have this kind of downstream stage of an electromagnetic centrifuge where we're going to spin out the various different ionized rare earths based on mass. And so here is just a very quick overview of the experimental setup. So we have kind of our ionization stage over here, and then that's going to then feed into this separator stage downstream. And so just a quick overview of the results. So here we effectively start out with a gas mixture that is half helium and half argon, and as we kind of apply this E cross B field to this electromagnetic field, we can basically achieve something like 10% separation with relatively low residence time. And similarly, as we use a molecule pair that has a smaller mass difference between them, then obviously the separation is less, but still relatively fast residence times. So with that, I'd like to kind of conclude and acknowledge our students. So Shayla Gerardo and Naveen Murugi-san has been doing the bulk of this work. And then, of course, our collaborators who have helped us with kind of doing some of the chemical analyses in the work.